Good morning, students. Today we shall see orthonormal basis, etc., and Gram-Schmidt process, and some problems on Gram-Schmidt process. Okay, the advantage of standard basis. We know that E1, that is 1, 0, and E2, 0, 1 are the basis, is the standard ordered basis for R2, right? So what is the advantage of this one? Suppose I take a vector 2, 3 in R2. I take a vector 2, 3 in R2. Immediately we can write this as a linear combination of these two vectors. How 2, 3 can be written as 2e1 plus 3e2. This is the linear combination. See here 1, 1, another vector 1, minus 1. This is also an ordered basis for R2. Is an ordered basis for R2. But suppose we are trying to write this as a linear combination of these two vectors. It's not so easy as the standard basis. Here we could find the coefficients very easily, like as 2 and 3. Here if you write, that will be difficult. Let us assume that will be already I did this one 1, 1, and another one basis is coefficient is this one. So these coefficients are is not so easy to find. Similarly, there is an advantage of finding orthonormal basis. So let us see now what is orthonormal basis. Dear students, the definition of orthonormal basis. Let V be an inner product space. A subset, say S, of this vector space V. This is called an orthonormal basis of V if these two conditions are satisfied. S must be an ordered basis. Like this is an ordered basis of R2. This is an ordered basis of R2. So like S has to be an ordered basis for V, for the vector space V, as well as S is an orthonormal set. Orthonormal set means what? The elements of S must be orthogonal to each other and all are unit vectors. See this one. This is an ordered basis, but this is not unit vectors, right? This is not unit vectors. But these two are orthogonal to each other. For example, consider this one. Already we have seen 2, 2, 0 and 1, minus 1, 0 and 0, 0, some 3. This is an ordered basis for R3. It's an ordered basis for R3 as well as orthogonal, but not unit vectors. So if you divide by this one by its norm, then it becomes an orthonormal basis for orthonormal basis for R3. Okay, now let us see a beautiful theorem. Just now we have seen that if the basis is a standard ordered basis, then it's easy to express any vector as a linear combination. But suppose if it is not an standard ordered basis, somewhat it is difficult to find these coefficients. However, suppose we have orthonormal basis or orthogonal basis. Let us now see how to find the coefficients very easily, directly by a formula. This theorem ensures that one. Let us see the theorem now. Let V be an inner product space and S is equal to V1, V2, etc. Vk be an orthogonal set of V, orthogonal subset of V consisting of non-zero vectors. If Y belongs to the span of this set, if Y is a linear combination of these vectors, then Y can be expressed as summation, let us say I varies from 1 to k, inner product of y comma vi by now vi square into vi. See, if y is a linear combination of these vectors, then the coefficients are nothing but this one only. This is the coefficients. So we could find the coefficients directly by some formula like this one. So now let us prove this statement. Let us prove the statement. Proof. Y belongs to span of S. So surely y is equal to summation I is equal to 1 to k ai vi, right? Now just let me find this one, y comma vj, inner product of this one. This is equal to summation I is equal to 1 to k ai vi comma vj, inner product. We all know that this summation can be splitted and the constant can be taken out. So this expression can be written as summation I varies from 1 to k ai inner product vi comma vj. But we all know that it is given that this is an orthogonal set. So this will be 0 until this I is equal to j. Otherwise this will be 0. When I is equal to j, we will get aj into inner product of vj comma vj. That is nothing but aj into norm vj square. So this one is this one only. So y belongs to span of S means y can be written as like this one. To find the coefficient is the duty. So the coefficient aj can be derived from this formula. Aj is equal to inner product of y comma vj by now vj square. Instead of this aj, if you put ai, here I only. Okay, so we have arrived this proof. So we have got aj, right? We have got aj. So ai means here it has to be I, here it has to be I. So substitute this aj in this equation. So y is equal to summation I varies from 1 to k inner product of y comma vi by norm vi square into vi. That's all. So if y belongs to the span of S, then okay, one simple question, why this non-zero vectors is given? Because here norm vj square is non-zero. This is non-zero for all. This is non-zero for all vj. Hence we can find aj as by dividing this one on both sides. Here this one is non-zero. That's why in the condition it is given. The condition it is given as non-zero. We have applied that one. So all the hypotheses, assumptions in the theorem must be used in the theorem, in the proof. You have to be careful. Okay, let us see one more thing. Suppose here, listen, suppose here this is an orthonormal set. This is an orthonormal set. Orthonormal set cannot contain the zero vector because zero vector is not a unit vector. So suppose it is an orthonormal set, then this denominator will be 1 only. So note if S is equal to V1 etc. Vk is an orthonormal set. Is an orthonormal set, and if y belongs to span of S, y belongs to span of S, then y can be written as summation I varies from 1 to k inner product of y comma vi into vi. So the coefficients are so simple to find, right? So if you have some orthogonal set and if y belongs to the span of S, then y can be written as like this one. Suppose V is an inner product space. V is an inner product space. V is an inner product space, and S is an orthonormal basis. S is an orthonormal basis. Then for every y in V, can be expressed as this one. So the finding coefficient is easy. Similarly, we are going to see later. We are going to see finding that linear transform, that matrix representation of the linear transformation corresponding to the orthonormal basis is so easy. It's going to be easy. That means we are going to find some such formula to find each entries of that matrix later. Okay, let us conclude now what I have said. So I have summarized this one. If it's a bracket, if V is an inner product space and S is an orthonormal basis for this vector space, then orthonormal basis means it is an ordered basis as well as orthogonal to each other and unit vectors. Then for each y belongs to V, y can be expressed like this. So y is a linear combination of these basis elements. But the coefficients, finding coefficients is so easy. Just take inner product with y. Simply you can find the coefficients. Now let us see Gram-Schmidt process. Before that, just let us see this one. Suppose we are given two linearly independent vectors. For example, we are given some W1 and W2 in R2. Consider this is R2. It is y-axis, it is x-axis. So in R2, we are in R2. Clearly this W1 and W2 are independent. Why it is independent? They are not in the same line passing through the origin, right? But see here, they are not orthogonal vectors. The angle between these two vectors is not 90. Actually, consider R2 with respect to standard inner product. Okay. Now consider this vector. Now, this is perpendicular, right? First one is, this is V1, it is W1, it is W2. Now consider this one. It is perpendicular. Now let me give new names. Let me give W1 is equal to V1. And let me take this new vector as V2. Okay, what is this foot of this point? See, this is W1. So this point will be some C times W1, right? Because it is W1. So if you take any point on this line, that will be like some C times W1 only, right? And this is C times W1. If you add CW1 plus V2, we will get W2. But our aim is to find V2. See here, my aim is W1 is given, W2 is given. Both are, it is an independent set. Now I wish to find orthogonal vectors. Instead of this W1 and W2, I wish to find orthogonal vectors so that the first vector generates W1 and the first two vectors V1, V2 generates W1 and W2. Okay. My aim is to find V2. V2 is equal to W2 minus CW1. But here we have to find C. Clearly V2 is perpendicular to this W1. V2 is perpendicular to this W1, right? So V2 inner product W1 or V1, let us put W1 now. This inner product is clearly 0, right? Now let us take the inner product. What is V2? W2 minus CW1 and this one. This is equal to 0. But if we expand this one, we will get W2 comma W1 minus, we can take C outside. So W1 comma W1, that is equal to 0. So what is C? C will be inner product of W2 comma W1 by norm W1 square, or C is equal to W2 comma, what is W1? I have put V1 only. V1 by norm V1 square. So we have found V2 that is perpendicular to this W1. So what is V2? V2 is equal to W2 minus inner product of W2 comma V1 by norm V1 square into W1. Instead of this W1, let me put V1. So just look at this one. We have, if we are given W1 and W2, they are linearly independent vectors. We are able to find some V1 and V2 such that this V2 is perpendicular to this V1. V2 is perpendicular to this V1, and to find V2, this is the formula. V1 is nothing but W1, but V2 is equal to this one. So this geometrical interpretation is going to be, can be extended to any number of linearly independent set, and that is called that is going to be called Gram-Schmidt process. This process is going to be called Gram-Schmidt process.